Did you say it's warm?
No, I said
You have a fork. You have a fork. All right. Okay. So, leaving the Earth. Remember yesterday, I said, oh, by the way, I can hand back the tests. I'm going to save that for the end of class. Remind me. If you don't get them back today, you'll get them back tomorrow. Okay, tests right there. So, listen up. Let me put this out of the way. Robert. How's it going? You ready to roll?
Yeah.
Got a pen, pencil?
Yeah.
Nice. Okay, so remember yesterday, I said that in my mind, when I kind of thought about how I wanted to teach this, I imagined this trek across the stars. That's the Star Trek thing. Anyway, but I imagined starting at Earth, that's our home base, obviously, and then we're going to proceed out from there, all right? So we learned about the Earth yesterday. We learned about its tilt, all right? We learned about the seasons. We learned about the force of gravity, how it decreases, but never quite gets to zero, but gets like super weak. And today we're going to then get off of the Earth's surface and eventually then encounter the next objects that we would encounter in space. So today I'm talking about things like satellites. Now satellites obviously aren't stellar or what we call celestial objects like the moon or another planet, but they are important to us, and they are kind of another reminder of how orbits work. Because when planets and things interact in space, they will often move in this kind of orbital fashion. So orbit becomes an important part of it. So we're going to leave the Earth today, and then we will eventually get out to the moon, and then that's where we'll stop today. And then tomorrow we will get into the planets. So, leaving the Earth. Again, we must overcome gravity. We've already talked about this. We've talked about how gravity gets weaker pardon me, excuse me, pardon me. We talked about how gravity gets weaker the further away you get from a massive object, right, like the Earth. What I want to talk about now is about what we need to overcome gravity. How do we get ourselves here on the surface of the Earth out into space, and maybe not all the way out into deep space, but maybe just even into orbit? That's our next thing we're encountering. And then ultimately maybe to the moon, how it's behaving, and then ultimately into space. So what do we need in order to get ourselves off of the surface of the Earth? Well, think about a rocket. How does a rocket get itself off of the surface of the Earth? Yeah, Danton? You use chemical energy and turn it into kinetic. That's a perfect answer. That's exactly correct. Where'd you get that answer? Just common sense? It's genius. That's exactly correct. We need energy, all right? So energy comes in many different forms. There are what we call potential energies, stored energies, energies that are stored in attractive forces, right? So gravity has energy. If you've ever tripped and fallen and hit your head, gravity's pulled you to the ground, turn that energy into motion and you hit your head, right? That's a type of energy. Chemical energy is stored in chemical bonds. So every time you burn a piece of wood, you're taking the chemicals that are in the wood and you're initiating a chemical change, which then releases the chemical energy. So those are different stored energies. Nuclear energy is another stored energy, all right? Stored in the nucleus of the atoms. And ultimately, you've got to turn it into kinetic energy. In other words, you got to get going. You've got to get moving, all right? So let's say you want to climb up a mountain, or perhaps, are you a skateboarder, Jay? You look like a boarder to me, no? I don't know. I have no idea what a boarder looks like. Anyway, imagine you're a skateboarder. You've all seen the TV shows of the guys on the skateboard, right? Okay. So you've seen it on some kind of a video of some sort, and in order for the skateboarder to get up out of the, is it a half pipe? Is it a bowl of some sort? Okay. See, I knew you were a boarder. Anyway, in order to get up and out of it, you've got to have some speed, right? You've got to be moving. And that's the kinetic energy, right? That's the energy of motion. So the boarder gets the speed by pumping their legs and using the energy in their muscles. And eventually they get themselves enough speed that they can get right up out of the bowl, do some tricks, that type of thing. If they're not very good, they might just get out of the bowl and crash or something like that. But they get up out of the hole or out of the bowl. Gravity is what is causing that skateboarder to come back down. And so that kinetic energy becomes this stored energy because of gravity. We call it gravitational potential energy. And the boarder comes back down and crashes to the earth. That's exactly what a rocket is doing. A rocket is like the boarder, except instead of using legs to push, a rocket into space, that'd be phenomenal, some kind of superhero perhaps. We use the chemical energy of a chemical reaction. We light that up. It produces what's called thrust, and it pushes the rocket up out of the bowl, or out of the gravity hole, we sometimes call it, or the energy well is actually the term we use. I've got a little, it's really I found this kind of cone thingy. You see it? It probably came from an old speaker of some sort that had these funny cones in it. But when I saw that, I thought of gravity. I know I'm a geek, but that's the way it goes. This is kind of like a representation of the gravity hole that is produced by an object like the Earth, or the moon, or the sun, or anything that has mass. So we learned yesterday that gravity is a force that gets weaker and weaker. Just like gravity is a force that gets weaker and weaker, when we're on the surface of the Earth, we're down at the bottom of the gravity hole, and in order to get ourselves away from the Earth, to get to that weak spot, we've got to have enough energy to get us up out of the hole. So what does a rocket do? A rocket will start way down deep in the energy hole. It will be pushed up, like being pushed up a hill, and if it doesn't have enough kinetic energy, it's eventually going to stop, and what's it going to do? Fall back to the surface of the Earth. A failed escape from the Earth. So I'm going to put this down here like this so I can kind of show you. If I could prop it up, maybe somebody got a textbook nearby? Let me grab a couple of textbooks here and just show you what we're dealing with. It's hard to see, but I just want to show you what we're looking at here. What's happening? What's so funny? What's that? Oh, silly, giggly grade 9s. So let me bring this up here. I'm hoping you can kind of see into the hole a little bit. Just a little bit, but that's okay. Marble, that's us, down on the surface of the Earth. We put a rocket on the back end. It goes straight up the side of this hill. If it doesn't have enough energy, rolls back down. No good. Failed escape. All right? What do we have to do? We have to get going faster. It's like we've got to pump our legs. So eventually, where's all my marbles? I got a bunch of different objects. So eventually, if we can give it enough energy, we can get it all the way up out of the hole and get it to this flat part. This flat part is successful escape from the gravity well. So you got to be going fast enough. We have a name for this speed that is needed to escape from a gravitational hole. It's called the escape velocity. All right? And the escape velocity for Earth, I have it on the next slide. We're going to write it down eventually. The escape velocity for the planet Earth is 11.1 kilometers per second. Don't write that down yet. I want to draw a graph first. 11.1 kilometers per second. All right? So for any object on the surface of the Earth, whether that is a rocket or Robert, if we wanted to send him to deep space, that object needs to be going at the surface of the Earth 11.1 kilometers per second. What's 11 kilometers from here? Anybody? You know what I always use? I'm from Watford, so we have this Alvinston to Watford road race that really, I don't know, it's painful. I ran it twice when I was a kid. It's 16 kilometers from Alvinston to Watford. So not quite that far, moving that distance in 1 second. That's pretty fast. That's a fast speed. So if an object is going that speed at the surface of the Earth, it will have enough kinetic energy, like the skateboarder, to make it out of the hole and be gone. It'll be gone. It may run into the gravity hole of another planet and get sucked in, and now it's stuck on another planet. Or it may get stuck in the gravity hole of the sun, because it's really big, the gravity hole of the sun, because it's so massive, all right? But to get away from the Earth, an object needs to be going 11.1 kilometers, not meters, but kilometers per second. What I want you to draw on this first one is another graph, all right? And this time, it's a funny graph because my x-axis is up here, just like my flat part. And this time, the graph, again, here's our planet right here. We're stuck on the Earth. Here, we're really down in the energy hole. And in order to get up out of the hole, we need to have some energy, all right? So this graph is energy on this side, energy, all right? And this, again, is our distance, the distance away. We called it R, okay? So again, if you are on a rocket, like a skateboarder, and you have a rocket that goes, yeah, and you get there with 0 velocity, not enough. You come back crashing to the Earth, okay? If you can get on higher enough, you can get further out, but nope, you'll come crashing back to the Earth, all right? Okay? So we exist in an energy hole. We're stuck on Earth. It's really hard to get off. If it was easy, we have all kinds of things in space, but it's hard, and that's why, you know, it's expensive, and you got to build all this equipment. It's really tricky to get out of the energy hole. Okay, so that's what we need in order to get ourselves off of the surface. Let's write a few things down here. Did the previous slide say getting into orbit the first time? No, leaving the Earth, getting into orbit. So now, let's talk about getting ourselves into orbit. Again, there's a little definition of energy. In this case, we're talking the chemical energy. Gives it some speed to put it in orbit or leave the Earth. Escape velocity, it's the speed needed for an object to leave a celestial object's surface and be gone and not fall back. In terms of the Earth, it's 11.1 kilometers per second. And the shirt I wore today, I actually got in Houston, Texas, when I went to NASA. We were down there about 3 years ago, and this is a cool shirt. It says escape velocity, and the fine print says you can't leave home without it. Because if you don't have that speed, you're not going anywhere. You'll notice this equation, and you don't have to know this equation again, but I'll write it down. The V, that escape velocity, is equal to 2 times the big G times the big M over the R, and then you have to take a square root. That's fun. I'm not going to make you do calculations with that. If you continue on and take grade 12 university physics with Mr. Petrus, you'll learn a unit on planetary mechanics, and you will derive that equation. It's fun stuff. I used to teach that course. It's a great course. You'll notice some of the things that we saw in yesterday's force equation is in there. The big G, that's that gravitational constant. That's the mass of the object. In this case, I'd put the mass of the Earth. This is the radius from the center. I would put the radius of the Earth because I'm standing on the surface of the Earth. And if I put all those numbers into that equation, I would get, actually what I would get is in meters per second. So I'd get 11,000 meters per second, right? Which I would then convert to kilometers per second. Okay. Now, at this point, I've talked only about moving straight up out of the gravity hole. That's not very smart. If we take our rocket and shoot it straight up, if we don't If we're not going 11.1 kilometers per second, what's that rocket going to do? Come straight down, back on where we shot it off. So that's no good. What do actual rockets do when they take off? How do they move? How do they move? Robert? They get an angle, and then they get going sideways. That's what it takes to get into orbit. Instead of just being shot straight up, if we then shoot it sideways a little bit, we then start to get this circular motion around the planet. Now, at this point, I was hoping for everyone to kind of see this better. So if you want to take a look at this, you have to stand up. So just stand up at your desk if you want to take a look. If those of you who are close, you don't necessarily have to stand up. But if you can't see this, you can just stand up here and just stand up and take a look. So here's what I'm going to do. I've got my various objects. These could be satellites, this could be the moon, etc., etc. And I'm going to send it towards the Earth, which is at the bottom of the hole. And when I do that, if I send it straight in, not exciting, crash straight on the surface of the Earth. But if I give it some sideways motion, that is awesome. That's just the best sound in the world, isn't it? You can see it goes around and around and around and around and around. Eventually it gets sucked in and it crashes on the surface of the Earth, all right? Now, in terms of a rocket putting something into orbit, it's the opposite. I would have to start at the bottom, give it some speed sideways so that it can get going around and around and around, and then can stay there. So again, if I started a little higher, oh, that was a fail. See how that dove right in there? Crazy crash. Crash, that's fun. I love that sound. Oh, that one had a little quicker one. Now it's going. What happens to the speed as it goes down into the well? What happens? It gets faster. Because just like falling off of the CN Tower, don't fall off the CN Tower. As you approach the surface of the Earth, you get going faster. Same thing here. You get going faster. All right? Now, exactly like skydiving, correct, but hopefully your parachute prevents you from crashing. So, let's now talk about orbit itself. Now, if I did it in reverse, we're not going to get to see this today anymore. All right. So let's now make this look more like an actual satellite. You guys are going to need safety goggles here. So just shield your eyes in case something comes flying at you. In order for me to simulate this, like leaving the surface, I've got to get this thing spinning and give it some energy. So let's see if I can. That's a fail. That's a fail. Here, I've done this before. I've done it. What if I start it like this? Oh, that's a fail. Okay. Oh, it's terrible. Oh, it's just so hard. Okay, that's gone. Anyway, okay. I'm going to stop at this point. So, I've got to keep giving it a little bit of a push if I want it to stay in orbit, okay? Obviously, I can't do that very well, but that's what the rocket does. It gets it up, it gets it going in a circle, and then it's in orbit. If it's way beyond the atmosphere of the Earth, it'll stay there. Nothing's going to slow it down. If it happens to get into the atmosphere, then the air drag will slow it down a little bit, and what will the poor satellite do? What do you mean? It'll fall towards the Earth. So when we put a satellite into orbit, we want it out of the air, so the air friction can't slow it down. If it were to get into the air, it would then slow down and crash into the center just like this. The friction of the ball on the surface of this is like the friction of the air. That's why it crashes in. Okay? All right. Also, things like the moon and the Earth, we don't have to worry about it spiraling into the sun because there's no air in space to slow it down. So it's got its energy, it's in orbit, and it's just going to keep on going. All right? So that's what orbit is. We're inside the well still. We're inside the well, but we're moving sideways so that we don't crash into the object that we're in orbit around. All right? Okay. That's fun. So let's, what did I want to, let's talk about a little bit here. So satellites, let's define what a satellite is. simply smaller objects that orbit around a larger object in a closed path. By the way, for every ball that I crashed in there, it wasn't a closed path because it spiraled in and crashed. If the path was a closed loop, then that ball would just stay on that same path, going around and around and around, and it would be true orbit. All right, it would be a true orbit. All right? We can have a satellite around the Earth. Earth, the big object. The satellite is the small object. The moon is considered a satellite of the Earth. It's a natural satellite created probably by a collision of a big asteroid with the Earth many, billions of years ago. That's what one of the theories is, but it doesn't matter. The Earth is technically a satellite of what object? Yep, the sun. The sun is the main object there. Is the sun as a star orbiting around an object? Any ideas? Some scientists believe that the center of our galaxy is a really big black hole, like a supermassive object that our sun is in orbit around, right? So there's a relationship there as well. Okay. All right. Let's talk a little bit about these different satellites. Did I want to talk about weightlessness? I had all these great notes in here. I do want to talk about weightlessness for a moment. So let's just hold off for a second. After this, I want to draw a little picture. Here is the Earth. Looks just like the Earth I drew yesterday. And now I'm going to have a satellite going around it. And my satellite today is the International Space Station. And that looks nothing like the International Space Station, but you get the idea. Now, a question was asked earlier on about there's no gravity in space. So I think it was Jessica. You were asking me about gravity at one point, right? You said, how could that work? There's no gravity in space. It was quite a while ago. That's okay. There is gravity in space. Remember, that graph of the force of gravity states that it gets weaker and weaker and weaker, and it never disappears, but it does get weaker. So then why do the astronauts float around when they're in space in something like the Space Shuttle or the International Space Station? Do you know the answer? What do you got? Gravity is pulling it down. If gravity was not pulling the International Space Station down, and that International Space Station was traveling with a speed, a velocity in that direction, because the rocket gave it a speed, if there was no gravity to pull it down, where would that space station go? Yep. Forever and ever off into space. And they'd be lost. And they wouldn't be very happy, the astronauts on the space station. So it's not that there's no gravity out there. Because what does the space station actually do? It goes in orbit, which is going to be an ellipse, probably a nice circle. Please draw that. So the question becomes, why does it look like they're floating? Do you people like amusement parks? I'm not a fan of amusement parks. Even when I was in high school, the roller coasters, I'm not a fan. But I see some of those awesome rides where they bring you up nice and high, and then they just hang you there for a while, and then zoom, they let you go down, and you lose your mind, that type of thing. And I guarantee some of you have tried this. You've either taken a coin or taken a little thing out of your pocket, and then as you fell, right, what's that? It would hover. It's like, oh, it's floating, yeah. And then you all scream, and you do it again, and it's funny. You wouldn't do that. You're a safety person. You've never done such a thing. Me neither. Okay, so what's happening? Well, when you have nothing underneath you, and you are able to fall freely through space because of gravity, we call that weightlessness, all right? You have no weight. The weight of your body is the force of gravity pulling down on you. When you stand on a scale, it measures your weight because the scale is squished because of the force of gravity on your body. If you were to take a scale on that particular amusement park ride, sit on it, look at the numbers between your legs. Before you fell, it would read whatever your weight is. All right? Let's say I'm 170 pounds. No, I'm not. I'm much heavier than that. But anyway, let's say it's 170 pounds. When that ride starts and the whole thing drops away from you, what's the reading on the scale going to be? 0. It's going to be 0. Because now everything's falling and you're not pushing down on the scale anymore. You're weightless. That's what it means to be weightless. All right? When you are in a roller coaster and you come over the top of the roller coaster and for a brief moment your butt comes off of the seat, you're weightless. There's nothing holding you down. Your body senses that as weird. Your stomach goes, woo, that was awesome, woo. That's you. You lose your mind on these things. I guarantee it. Would be awesome. Anyway, so have you ever seen the videos of the training planes that they bring the astronauts in and then they do something with the planes and then all the astronauts float around in the plane? Have you ever seen that? Here's what they're doing with the planes. They're taking the plane. If you've ever studied the way an object moves in space, if you were to throw a baseball, it makes a nice curve like this. It's called a parabola. All right? You'll learn about parabolas next year. They're awesome. Anyway, what they do with the plane is they take the plane, they fly it up really steep so everybody's squished down in their seats, and then they fly it through a parabola curve. In other words, they're launching you like throwing a baseball and then letting your body fly through the air like a baseball being thrown. The only difference is the pilot is awesome and he's flying the plane around your body as you're being flung into the air. And there's weightlessness for an elongated period of time. So they float around a little bit, it's kind of fun. And then in the end they have a red light and they say, get to the floor of the plane. And the reason is, if the plane were to continue on this path, what would happen? Yes, death and mayhem. That's bad. So what does the plane do? It goes and does that. You now pay for the weightlessness because now you're being squeezed down to the bottom of the plane. Just like if you're in a car that takes off quickly, you get pushed to the back, you feel this extra weight. So, what's happening to the astronauts in the International Space Station? Well, they are falling due to gravity. The force of gravity is there, right? That FG. They're falling due to gravity. They're falling just like a baseball falls towards the Earth, just like the plane is falling towards the Earth. But they're moving so fast sideways that as they fall towards the surface of the Earth, they miss the Earth. They never crash into the Earth because their sideways speed is so great that they, let's say it was an inexperienced astronaut. Oh my God, I'm crashing towards the Earth. This is terrible. Ah! Oh, I missed the Earth. Oh, that's good. I'm not going to die, boom, boom, as Jay's been saying. I'm not going to die a horrific death. So what happens? I'm falling towards the Earth. Oh, I guess this isn't so bad. I'm falling towards the Earth, but I'm going sideways so fast, I never hit the Earth. So just like in the plane, they're falling all the time, but the satellite is moving with that falling object, and they never hit the Earth. And because they're all falling together, there's no force on their bodies, and they feel weightless. Yes? To adjust it. If something slows them down, then they're on a spirally collision course. You sometimes have to put a little more energy back into that to bring them up. So let's write a little bit about being weightless, and then I'll answer some questions. So, no weight on objects in orbit. All right? As the object falls, and when I say object, I could mean the space station itself, could be the astronauts, could be all the equipment that's in there. As the object falls down, it also moves, I'm just going to say sideways, and misses the Earth. All right. Moves sideways and misses the Earth. That's exciting. So there is gravity there. If there wasn't gravity, they'd all float away and be gone forever. They'd never come back. So there is gravity on all those objects in orbit. Same with the moon. There's gravity on that object as well. But because it's moving sideways so fast, it never strikes the Earth. Okay? Are we okay with this idea of being in orbit? Well, maybe you wouldn't like it very much. I think it'd be awesome, but anyway, of the way it works. All right. Oh, and this is, by the way, what it means to be weightless. This is what we call weightless. Weightless is different than no gravity. Gravity's there. It's just you're not feeling the effect. All right? It's like you're on one of those amusement park rides that infinitely falls. After a while, even Jenna, after a while, would be like, yeah! This isn't fun anymore, right? You'd eventually get bored of it, all right? Question.
So it takes 11.4.
That's to get completely away.
But how much does it take to get back in?
Oh, it takes nothing. You just have to get close enough and then let gravity do the rest of the work. And then if you just let gravity do the rest of the work, you'll be going 11 kilometers per second when you strike the Earth. That's why you want to come in at an angle. That's why when the astronauts come back to Earth, they don't go, okay, let's go home, crash. That would be bad, right? So what they do is they kind of slow themselves down, and then, oh, they're speeding up, but then the atmosphere slows them down. Heat gets involved, and it's like putting on brakes, right? If you've ever worked on a car, right? Allie, you're a gearhead, right? You work on a car. So she knows that the brakes work by squeezing the brake pads, and then they get hot. So the car's movement energy turns into heat energy, and then you slow down safely. In order to stop your car, you don't just like run into the back of your garage, right? That would be a good way of doing it. It would work. Ah, here I come. You know, you'd lose the energy, but it would be dangerous. So they got to do the same thing. They got to put the brakes on, and they use the atmosphere as the brakes. All right? Yep.
Do they feel like that weightlessness?
A missile?
Like a missile. Like, does it feel like weightless for a second and then like it's right back?
So instead of using, say, the word missile, we could use rocket. We could use anything. When you can write this information down, please. Write this information down. Oh, I'm never going to get done this lesson. So, just like when you're at a stop sign in a car, right? And Allie, the gearhead, steps on the gas because she's like souped up the car. You'd get pushed way back in the seats, right? You'd feel a pushback. You'd feel heavy in the seats. That would be the same in the rocket. When the astronauts take off, they're squeezed back into the seats because they're being accelerated up into the air. As soon as that rocket has gotten high enough and they shut it off, like a missile or like a rocket, then it's now being launched like throwing a ball, and at that point they're weightless. Because now it's floating up, it's going, and it's hopefully going sideways enough that, am I going to crash into the Earth? No, it misses the Earth. Whew, successful orbit, and away it goes. Right? What's that?
They burn on like contact. They slowly burn.
When they come back in, they encounter the atmosphere, and hopefully their protective devices keep them alive, but that's the same as hitting the brakes, turning the kinetic energy into heat. Okay, artificial satellites are man-made. All right, just 1 second, I'm going to just talk about this, and I'll get to you. There are many types of orbit that we can have. Low Earth orbit. What's the speed of these guys in low Earth orbit? Think about my well when I drop those things in there. What happens when things are close to the surface to be in orbit? Yep, it speeds up. So satellites in low Earth orbit have to be traveling how? Sideways, fast, really fast sideways, all right? When you look up at the night sky and you're having a camp, whatever, fire, and you look up there and say, hey, look, there's a satellite. We've all seen that before. When I was a kid, it was rare because there weren't very many satellites, but now there's all kinds of them. You can see them all the time. Those that you see zing across the sky, low Earth orbit satellites. Okay? They're really moving. And they have to, because they got to stay in orbit. They're so close to the Earth, if they don't go fast enough, they're going to hit the Earth. So they got to really be going to miss the Earth. All right? So these guys are fast. Okay? As you move higher up in orbit, they travel slower. Oh, you can see there, fast orbital speed. I didn't even notice I had that there. Types of things in low Earth orbit. The International Space Station, it's fast. They go around the Earth, I think, once every 45 minutes or something like that. Like, they're zinging around there. The Hubble Space Telescope, also low Earth orbit. And Earth observation, spy satellites, that type of thing. I'm getting that out of a textbook. I really don't know that. There's other satellites I've seen that are like that. Communication satellites and GPS satellites can also be down there. All right. Let me move the next one here. Yep.
When planes are going by, they like feel the heat
Of the atmosphere.
Yeah.
They're getting warmed up. They're pushing the air out of the way.
Yeah.
That's why they got to keep pushing so hard with their engines.
So when people are like skydiving, do they feel the heat?
They would feel that, you bet. It wouldn't be as much as they're not going nearly as fast as a plane or something coming in from orbit. So they're not going to burn up. But they would take some of that energy. Their temperature would increase. Okay, folks. Now, there's a medium Earth orbit as well, but you get the idea. The higher up you go, the slower it is. This orbit is a very special one. This orbit is at a certain height that the time it takes to go around the Earth once is 24 hours. Now that's a slow orbit. But notice that 24 hours is exactly the same amount of time that it takes for the Earth to go around once. So I've got a picture for this that I want to draw. Again, anybody know what this is? Very good. See, I am so good at drawing the Earth. You guys know that that's the Earth. I'm going to put on the axis with a little bit of tilt on it. I'm going to put on the equator, okay, because I'm such a good artist. And now I'm going to put one of these satellites way up above the surface of the Earth, and I'm going to put it out here. Little satellite way out here. Doesn't matter what it looks like. That's a little box with some lines, because I'm such a good artist. And it's going to go around its orbit. So there's the extent of its orbit. It's so big that it's going to go way around here, and it may come around the back. And it's going to take 24 hours. Now, let's say that I am standing right below that. This is me on the surface of the Earth. Please draw me. And I am on the equator. I imagine I'm in Ecuador. Equator goes through Ecuador. It's a true statement. Yeah. Okay. Now, how long is it going to take me if I stood still to get around one rotation of the Earth? Yep. And how long is it going to take that satellite to go around its orbit? 24 hours. Which means if I drew a line from the center of the Earth out through me, it should point directly at that satellite. And if I want to see that satellite, where do I have to look? I'm on the equator. How much up? Very up. 9 degrees? 90 degrees. Directly up. It would be right there. And all day long, where would the position of that satellite be? Right there. It would never change its position with respect to me on the Earth. That's super, super important. If I have a satellite dish, because I want to watch satellite TV, I don't want to have to take my satellite, you know, at night when you see the light spots go across. Okay, we're losing the channel. Oh, jeepers. That was tough. Oh, here's another one. Impossible to do. But if you put a satellite that's at that point where it's 24 hours, how do I have to hold my dish? Straight up. Do I have to move it? No, I can put it on a post. I can walk away. I can connect the wire to my TV, and I can watch TV all day long without having to move my dish. No. Yes. Satellite.
The dish gives cable.
Oh, you mean like country cable? Because like we're out in the country and we don't have like cable in town? Yeah, you're right. Country cable's right. Okay. Now, we don't live on the equator. We live in the northern hemisphere. So we live up here somewhere. There's northern hemisphere me. I'm blue. And so it's hard to see me. It's winter. I'm cold. So I have to point my dish which way? Do I point it straight up? No. I point it over there. So here in Petrolia, we point our dishes to the south and about 30 degrees up, because that points to those satellites hanging over the equator, not moving. Super prime real estate in the orbit world, because that's where all the satellite TV goes. All right? Communication satellites. Okay? That's kind of neat. Yep. No one really owns the space.
No, like the satellite that gives you.
Well,
TV on.
the company that you get the satellite from, like let's say Shaw, or is there any other? Does Bell have satellite anymore? Maybe not. Down in the States, there's DirecTV. There's a bunch of them. They would pay to put that satellite up in space.
Oh,
They had to pay someone.
almost.
Well, no, they would have paid someone to put their satellite in that spot.
So there's like 5 satellites in the same spot.
No, it could be anywhere on the equator. So you've got that whole ring worth of stuff. But because we're in the Western Hemisphere, you're not going to put one over on the east side of the world because we won't be able to see that one. So Shaw in Canada is going to put it on the west side of the world, right? But other side of the world, they're going to use that side of the space, okay? All right, the moon. Whew, that was fun. So the moon is also a satellite. It's a natural satellite. It orbits a planet. Many planets have moons, right? Some have, in the tens of moons, 60 moons, I think, for Saturn or something. I don't know exactly. They're always discovering little tiny moons around there. The numbers are changing. Its orbital period is 27.3 days, which means, I'm going to draw a little picture. We all know what that is. Oh, we don't. I made it too small. It's the Earth. You're right. Let's put an E on that guy. And now I'm going to put a littler one. That's the moon. And it takes 27.3 days for it to go around once. Gee, that's about a month or moon.
But
I'm not joking. It's a real thing. The word month comes historically from the period it took the moon to go through all of the different phases, from full moon to full moon. Well, because kings and people like Caesar Augustus and guys like that who thought they were really important screwed around with the calendar and messed things up. So it's close. All right. Notice the period of rotation is 27.3 days, which means as it revolves on its axis, it takes the exact same amount. Which means as it goes around, it's spinning around at exactly the same speed.
that's like it's dropped.
Nope, it's not being thrusted in any way. As it goes around, it's also spinning on its axis at exactly the same speed, which means as it goes around, it's rotating along with it going around, which means we see the same side of the moon always. If it was rotating faster, we should see different craters at different times because it's spinning so fast, like the Earth. Like if you could sit on the sun, it'd be hot, but let's say you could sit on this sun right here, and you watch the Earth go around, that Earth is going like this as it goes around. But the moon is spinning at exactly the same speed as it would take to go around, which means it spins as it orbits, and so we always see the same moon in the sky. We never see the backside of the moon. We can't see it because it doesn't rotate fast enough. So every time you look at the sky, you look at the moon, you should wonder, why does it always look the same? It's because it spins at the same speed at which it rotates. All right. So we always see the same side of the moon from the Earth. That's fun. All right, let's talk about the phases of the moon. So, I guess we talked about going out towards the moon, but now I'm asking you if you could return back to Earth just briefly so that we could look out at the moon to see what we see. And you would see that that moon changes, once every 27.3 days. And that's because as it orbits the Earth, the sun strikes it on a certain side. Now, I made these notes up myself. If some of the wording is really bad, I'm seeing Grace looking in kind of a funny way. The moon and the planets, see, there it is. And the planet is, I guess could be R, right? Is that what you're thinking of? The moon and the planets, they're non-luminous. They don't produce their own light. So the moon is not like a star, and the Earth is not like a star. These planets don't glow. They simply reflect light from the closest star in this case, the sun. So as the moon goes around the Earth, we can only see the illuminated, the half of it that's being shone on by the sun. And so as the 27 days go by and it goes around once, we can sometimes see the moon completely illuminated. We can see the side that's completely, bright. And at the other extreme, we can't see it at all because we're looking at the dark part. It's not illuminated, all right? And it's kind of hard to explain, and I'm going to try to do it with this particular device here. All right, now I'm not going to use this. This is, ignore that here. Ignore that, because it's in my pocket now. Put this here. Put this here. All right. So, see, the hole is great, but why don't they have the hole pointing this way? Yeah, I don't know. All right. You get the idea. So, this is the Earth. See, it's kind of tilted. And this is the moon. This is the sun. It's not to scale. The Earth is not this big, nor is the moon. But you'll notice as it's got a bunch of gears on it, which is cool. As I bring it around the whole year, you can see the moon just kind of snakes around there. See that? And there's the Earth spinning like crazy, days upon days. There we go. And depending on where we are on the Earth, and depending on where the moon is around the orbit, we're only going to see a certain half of it lit up. A full moon is when that moon is right on the opposite side of the Earth so that it's completely illuminated. And here we are, if we're here on the surface of the Earth, we can see that completely illuminated moon. All right? If we're here on this position, the illuminated side is here, we're over here, we can't see the moon because it's not illuminated. It doesn't have any light on it. And you know what? It happens during the day. Because if the sun is shining on us right here, it's the middle of the day, the moon is out there, but we can't see it because it's the dark side of it, all right? When we get halfway through, all right, zoop, there's the sun, or the moon, it's being illuminated, but we can only see it half on, so we see that, what we call the half moon, because we're staring at the dark side and the light side. Yes? That it's going to absorb some of that particular energy? I would say yes, but then the heat will be re-radiated out into space. just like your hot coffee, your coffee drinker, right? I can tell. Just like your hot coffee cools down, right? If the moon gets a little bit of energy from the sun, it will eventually start to radiate that energy off, and there'll be a balance. The moon will have a particular temperature to it. All right? So there'll be a balance of hot and cold going on. Okay? All right. Let's write down some of this information about the phases of the moon. Don't write that diagram. All right? You've already got the heading, phases of the moon. There's another picture of it. I got two of them, but don't write it. Here's what I want you to write. All I want you to do is be able to name these phases in order. All right? So here's the way it's going to look. We start the cycle as a new moon. That is not the full one. That's the one we can't see. So what I want you to write on your page, and it can be just underneath here, I want you to put just a blank circle, and I want you to write new. All right? Now, so here we are, new, in new. We can't see anything. Now, as we proceed in the rotation, we can start to see a little bit of that lit part, and it looks like a crescent. Call that the crescent moon. Now, the word waxing means to grow, and the word waning means to decrease, which always bothered me because my first name's Wayne, and waning means to decrease. It was very kind of demoralizing. But anyway, waning means to decrease, okay? All right, so you'll notice that we go then to the waxing crescent. Now, students always want to know, which side do I put the crescent? There's a silly rule to this. First, let's draw the crescent, zoop, and we'll put waxing, and it's a crescent. All right, crescent. The tail end one, the last one, down at the bottom just before our next new moon, will be the waning crescent, and you'll notice it's on the other side. What letter does the waning crescent look like? What letter of the alphabet does a waning crescent look like? It looks like a C, right? Looks like a C. What letter does the waxing crescent look like? Nope. What if I put a line right there? It looks like a D. Which one comes first? The waxing does. No, it doesn't. It's the D that comes first. That's backwards, isn't it? Wouldn't it have been great if it was the C and then the D? But it's not. I used to do this in my courses all the time. When you learned something that you wished was the other way, but it's a backwards rule. C comes before D, but when it comes to the phases of the moon, D comes before C. That's how you're going to remember it. When it comes to the phases of the moon, D comes before C. That's how you're going to remember. It's backwards. It's a backwards rule. So, the D is growing to a full D. It's awesome. It's called the first quarter. First quarter. Which is funny because it looks like a half. But we are actually only seeing a quarter of the moon illuminated. Now, after the first quarter comes the waxing gibbous. I'm not even going to write that one down. I looked up the word gibbous. What the heck is a gibbous? It says something greater than a half circle, but not completely a full circle. That's the definition of a gibbous. It's useless. It is exactly what it is, but I'm not worried about the gibbous. So, after the first quarter, if we skip the gibbous, we get to here. Oh, that's supposed to be illuminated. Might look different when the way you draw it. You might make your pencil one look dark and the other one look illuminated. See what I mean? That's dark and that's light. This is the full moon. Full. Now, As we keep going, now this side starts to disappear. We get the waning gibbous, such a bad word. And then eventually we get to the C, which looks like a backwards D. But if I ignore that, looks like a letter C, and there's a backwards rule. When it comes to the phases of the moon, D comes before C. It's crazy. This is our last quarter. And then at the very end, we now have that letter C, which is the waning, not spelled like my name. Mine's like Gretzky, by the way. Okay. Waning crescent. That's what I used to tell people. And then the movie Wayne's World came along. And then it became less cool. But then the movie Wayne's World became super cool. So now Wayne is cool again. All right. Okay. So those are the ones I expect you to know in the order. That's the start of the cycle to the end, and then back to the start of the cycle. Okay. So if you're outside and you're looking at that moon, and you're saying, "Wow, that looks like a C." Well, you'd think that that's at the start, but no, that's at the end of the cycle. It's going to keep waning. All right? Or if you see a D and you think, oh, that comes after C, but wait a minute, it's backwards. That means it's waxing. All right? Okay? Yes, sir? Oh, look at this guy. This guy is knowing exactly. You must have cheated because my next thing is about the eclipses. Woo! Okay, first let's write about some special moons, though. I know, but I'm an elite teacher. I can squeeze some teaching in. Yeah, no, tomorrow. Pluto's tomorrow. Okay, the test. That'll be tomorrow, too. We'll be fine. Everybody will be okay. You'll be all right. Let's write down some special moons. You may have heard some terms. They'll say something, oh, look, it's a harvest moon tonight. It's beautiful. Let's go for a walk under the harvest moon. All right, you may have heard that. The harvest moon is simply the full moon that is closest to the autumnal equinox. In other words, it's the closest to the big first day of autumn. That's simply what the harvest moon is. You may have heard of the term blue moon. That happens once in a blue moon. That's what the saying is. What's that? That's actually the saying. Because it's very rare that 2 full moons happen within a calendar month. But it does happen every once in a while. Okay? Because remember, it's 27 days. So if you get a new moon on or a full moon on like the 2nd of the month, and there's, 30 days, you're going to get another full moon before that month turns over. They call that, the second one they call the blue moon, the second full moon of the month. And it's rare, so that's why they say, well, once in a blue moon, that might take place, that might happen. All right? Okay. I want to get to one eclipse picture for you guys. And then I'm hoping maybe you can do the other one maybe for homework. That'd be fun. You're going to need a ruler. Time's happening here. See if we can do it without a ruler. Let's see. We're going to test your straight line drawing ability. That's awesome. Okay. And I thought this was going to be a short lesson. Tomorrow, we're never, ever going to get done. Oh, Rachel's learning her song for tomorrow. And she wants me to put it on the internet, I think is what she wants to do. I'm going to have to get a second microphone. Ladies and gentlemen, I've got a guest for today's podcast. Okay, let's continue. The eclipse. So what's happening during an eclipse? Oh, goodness, we have the answers? That's exciting. What's happening?
Like the moon crosses in front of the...
Correct. It's quite rare, especially for a solar eclipse, because the shadow the moon casts on the Earth is really a tiny little dot. So you've got to be right at the right place on the Earth when that thing comes in between. And that's why solar eclipses are so rare, because you've got to be right in the right spot of the Earth. People will travel great distances to get under there to see the eclipse. We had one about 3 years ago, but it was partial. We weren't right in the dark part of the shadow. So let's try to draw this up. By the way, what is this? The sun. Very good. The big one. Sun's the big one. And this? Moon. And this? The Earth. And I know you don't have perfect circles, but you can do it. Now this gets a little tricky. And this, if you've got a ruler, it would be great. I don't have a ruler here, so I'm going to do my best. Some light that comes from the edge of the sun is going to graze the moon and is going to strike the Earth. So I'm drawing a line that goes from here to there to there. Whoa. Did you see that? See that line I just drew there? That is a line, baby. Right there. Winner for me. And some of it is going to go around the other side of the moon. Ooh, look at that. Look at me. Now, take a look there. There's the shadow. And you might think, hey, it looks like half of the Earth is in the shadow. But the sun is so big that the top part of the sun also makes a shadow. So it's an overlap of two shadows. So the sun's edge makes a shadow that way. This edge will do the same. Oh, look at me. Look at me. That's years of teaching. What's that? Yes, it is. Very good. And now I got the same one on the other side of the moon. Whoa, that one wasn't as good. Oh, that's not too bad. Nice. Now notice, in this area right here, I am in the shadow of both edges of the sun. This area right here is super dark. All right? And that's the good spot. That's where you see that perfect solar eclipse. All right? We call this dark spot the umbra. It's the umbra of the shadow. If you're in these other areas, you see just partial eclipse, like the moon just kind of grazes the sun there. So if you're in these other areas, and it's called the penumbra, don't worry about it. It's where it's not quite as dark. Now, for your homework, there is homework as well, but for your homework, try to do the lunar one, the lunar eclipse. All right? What's that? Have a lunar eclipse? That's fun. In the lunar eclipse, the sun and then the Earth gets in between that and the moon. So the same thing's going to happen. Two rays are going to graze the Earth, and two rays are going to graze the Earth, and we will see then the moon get all shadowed. I have no idea. Was that what you were going to call me on? Yeah. Marshall? I have no idea. Thank you. All right, see if you can do a lunar eclipse. And there's 2 or 3 questions out of the textbook as well. There's 2 or 3 questions, but it's like this. If you get this done, then we're in good shape. Any questions? Jessica, you've been dying. You've been so interested in this lesson today that you've gathered up all your questions. What are they, Jessica? None whatsoever. What do you got? In like minutes? No, it's not going to happen. No, it's not happening. Yeah, if you go to Google Classroom, it should be there. The questions are also right here, I believe. Right there. It's just 12 and 13, page 238. 12 and 13, page 238. Okay, I'm going to stop the recorder here. All right.